Alright guys, we're going to be talking about derivatives of parametric functions today. While you're watching this video, before I give away any punchlines, I want you to pause the video and think about what's coming before it actually gets here. I want you to give yourself a chance to think about what I'm asking before you see me produce any solutions. So at every step in the notes, I want you guys to try it, and then in the problems itself. Alright, so what we've been graphing are these parametric functions. So we have x as a function of t. Okay, x is a function of t. And we have y as a function of t. Okay, and so I know that looks a little convoluted, but what does that mean? That means when I have my x, I have x's with, I have t's, I have x equals stuff with t's in it, and I have y equals stuff with t's in it. And that's what I mean when we have x as a function of t and y as a function of t. When everything is said and done, when we've graphed these functions, which was our first part of parametrics, is we're left with something that we can relate to in a rectangular form, whether it's a parabola or a line or a circle or an ellipse. But we're left with something that still has it has a rectangular equation, and not only that, is that when I'm done and I look at the picture, I could talk about this, I could draw tangent lines, and I could talk about the slopes of those tangent lines, which is where we come into our need for our dy dx. We can talk about the slopes of the tangent lines. Those graphs that you drew have concavity. We can talk about the concavity of the graph, or the second derivative, but we need to figure out a way to come up with those things. Now, given the fact that x is a function of t and y is a function of t, I can't just find dy dx by taking the derivative of your y function, because if I take the derivative of this function here, I'm not going to be left with the derivative of y as a function of x, or with respect to x. If y is stuff with t's in it, when I take its derivative, what differentials would I have involved? Okay, and the differentials that I would have would be a dy dt, okay, because I have y equals stuff with t's in it. When I take its derivative, I'm going to have the derivative of y with respect to t. How about on the other side, with my x? Okay, if I take the derivative of this x stuff, what differentials would I have involved when I take those derivatives? Well, it would look like, okay, because x equals stuff with t's in it, when I take the derivative, I have the derivative of x with respect to t. How am I supposed to get a dy dx out of that? Okay, again, that's my goal. I want a dy dx. How am I supposed to get a dy dx out of that? Well, think about how to manipulate those two differentials, because if I take the derivative of y, I get dy dt. If I take the derivative of x, I get dx dt. How can I manipulate those differentials so I get dy over dx? And what I want you guys to do is think about those differentials as algebraic pieces, and how can I manipulate them to get dy dx? Pause it, come back to me. Okay, if I take dy dt and divide it by dx dt, we can manipulate those differentials so that we get a dy dx, okay? And what would happen is, when I have a fraction divided by another fraction, it's the same as the first fraction multiplied by the reciprocal of the second, and that would look like this. Okay, so, and then what happens here when I have that fraction divided by another fraction multiplied by its reciprocal, is that our differentials actually divide out. Okay, so those two differentials divide out, and I'm left with just dy dx, dy on top, dx on bottom. Another way to look at this over here, this dy dt over dx dt, is just to look at it as y prime over x prime, which would look like this. Okay, but the gist of it is you're taking the derivative of the y component and dividing by the derivative of the x component, and that'll get you dy dx. Okay, moving on to the second derivative. And I think I might do this on a new piece of a new screen because it gets a little confusing. I just want to address, before we get to second derivative, what else I've written on here. We can use these two formulas to find slope, concavity, tangent lines, etc. And if a curve intersects itself, there can be two tangent lines at a single point. And if that is the case, you're going to find which two tangent lines or which values of t, result in the same coordinate, and then evaluate the slope at those points. Okay, so it's pretty basic. Okay, so what we have here is that our dy dx is y prime over x prime, or the derivative of the y component divided by the derivative of the x component, and our second derivative we're going to talk about. Okay, for second derivative in parametric form, I would have d squared y over dx squared, okay, or d2y over dx squared, whatever. So my second derivative, I normally find by taking the derivative of the first derivative, and that would look like this. Well, before I show you, if my first derivative is with respect to t, then I'm going to have to, right, my first derivative has a bunch of t's in it. Y prime is a bunch of t's, x prime is a bunch of t's, so when I do y prime over x prime, I have a bunch of t's. So if I take the derivative of my first derivative, it's got to be with respect to t. And you guys will see exactly what I'm talking about when we do an actual example. So the derivative of the first derivative would have to look like this. Okay, so it'd be the derivative with respect to t of dy dx. Now, if we continue to think about these differentials as little algebraic pieces, if I think about what I have here, I have a d dy, or d squared y, over, in the denominator, a dt times a dx, which is not what I'm looking for. What I'm looking for is this. Right up here, okay? So it needs improvement. So now what can I use, and think about what we did for first derivative, how can I manipulate this algebraically to get this, okay, to get my d2y over dx squared. Okay, I want you guys to think about what I'm going to have to do to this to make it. Pause, think about it, think about our little components that we used to find our first derivative, and what we did to find our first derivative, and come back to me. Okay, the answer is to do some division, and we're going to divide this by dx dt. Okay, and if you think about what that would be, okay, I can see I have another fraction divided by fraction situation, and that means I have my first fraction multiplied by the reciprocal of the second, so that looks like this. Okay, and what I would have again is I would have differentials divide out, so the dt on top would divide out with the dt on bottom, numerator and the denominator, and I would have my second derivative, my d2y over my dx squared. Okay, so what is this in conclusion? In conclusion, I'm taking the derivative of the first derivative and then dividing by dx dt, which I see right here. Okay, so it's the derivative of the first derivative divided by dx dt. That's how I find a second derivative. All right, while you're working through this problem, just realize that I left enough space for you on the next side of the worksheet for you to, because there's not enough room for you to do A, B, and C on that little bottom piece of paper. In any case, so we have a curve C given by x equals t squared and y equals t cubed minus 3t. I want you guys to start by graphing it in your calculator. Play around with your t values so that you have a complete graph. You're going to start by seeing part of a Nike swoosh, but that's not a complete graph. And part of the indication for that is that it says that there has to be two tangents at the point 30, okay? And if you have a graph that doesn't cross itself, there can't be two tangent lines at the point 30. So play around with your t-values until you get a graph that crosses itself. Pause the video, come back to me, and I'll show you the big graph. Okay, I can visually see that the curve crosses itself at the point 30, okay, and that point 30 is an xy coordinate, and I have two tangent lines. If you saw the way that the graph is developed, okay, first I come through this way, and then I come around and come back through this way. Okay, so that's why I have two tangent lines. Because the first one comes this way, and the second one is when the object moves that way. It's not perfect, but I've attempted to graph the two tangent lines for you. Okay, so I see that the curve has two tangent lines at 30. We understand why it is, because I start by moving up and to the left, and then I go down and then up and to the right, and that's where my second tangent line comes in. To find the equation of those tangent lines, I need a point, which I am given. I have a point 30, and I also need the slope, okay? Let's find the slope by using the formula that we found in the first slide. So the slope is dy dx, and I find dy dx by doing dy dt divided by dx dt. So go ahead and find dy dt and divide it by dx dt, and pause the video and come back to me. Okay, this is what we should have come up with. We have 3t squared minus 3 over 2t. Now, I'm finding the equation of tangent line at the point 30, okay, and that, like I said before, is an xy coordinate. If you look at this equation that you found for slope, having an xy coordinate is completely unhelpful to you because you have t values here. So you're going to need to figure out what t values are going to produce that xy coordinate. Okay, so think about how you're going to have to do that. Pause and come back to me. So I'm going to have to set the x-coordinate equal to 3 and the y-coordinate equal to 0 and solve and look for common t-values. That's going to look like this. Okay, so I'm setting the x-coordinate equal to 3, the y-coordinate equal to 0. I'm going to solve those equations and I will get these results. Okay, so for x to equal 3, I have t equals plus or minus radical 3, and for y to equal 0, I have t equals 0 and t equals plus or minus radical 3. Okay, I see that I have the plus or minus radical 3 in common, okay, which makes me think that those are my two t values, but why do I have this other t value where the y-coordinate is 0? Well, look at your graph, think about it, and come back to me. Okay, and the reason is because of this coordinate right here, this point on my graph where my y-coordinate is also 0. So I have these 2 points right here where the x is 3 and the y is 0, and then I have this other coordinate here where the y is 0 but the x is not 3, and that's why that point is not important to me in this situation. Okay, so now that I have the t-values that give me the right slope, I can put those t-values into my slope equation. Okay, so I'm still working with the 0.30, but now to find my slope, I'm going to have my slope at t equals square root 3 and my slope at t equals negative square root 3. Calculate those values, pause the video, and come back to me. Okay, so this is what we should have come up with for our slopes. Okay, the slope at t equals square root 3 is 6 over 2 radical 3, which can simplify to 3 over radical 3. And I know I say to never rationalize, but in this case it actually benefits to rationalize because I end up with a much simpler slope. And then at t equals negative radical 3, I just have the opposite answer, negative square root 3 for my slope. Okay, so now to find the equation of a tangent line, now that I know a point and a slope, I just use my line equation and find the equations of the lines. So go ahead and do that and come back to me. Okay, so these are the two equations of the tangent lines. Y equals square root of 3 times x, quantity x minus 3, and y equals negative square root of 3 times the quantity x minus 3. Remind me in class that we'll look at these equations on WinPlot, or if you want to download WinPlot on your home computer, you can do that. And that allows you to both graph the original parametric function and these rectangular equations on the same graph, and you can see the tangent lines. I'm going to have to abandon this video and start a new video because I am running out of time. So see the next video for the answers to parts B and C.